Let's continue this. I'm back. I'll finish up chapter 3, section C, questions. So I think I'm starting to get a bit tired, but I should be able to get through this fairly easily. It's only about 5 questions left. So consider this. A is a 1 by n matrix, which means it's a column vector. And C is an n by p matrix, and show this is true. I mean, like, when you look at this, you just think, well, this seems like very clear cut exactly what's going to happen, right? So when you multiply this column vector A by the matrix C, you're going to multiply by the first column, take a dot product with the first column of C, and then a dot product with the second column, and so on, until you dot product it with all the columns of C, right? And then what's going to happen is you're going to take, let's say, the first element of the column vector and multiply it with the first element of the first column of A, and then the second column, and then so on. So what you're going to get is something like this, right? Such results like A1 times C11 plus a bunch of other stuff, and then A1 plus C12 plus a bunch of other stuff, and so on, until A1, C1, and let's say plus a bunch of other stuff. So then you know that you can factor this A1 stuff out. It's just A1 times the first row of C, because this is what these are. This is the first row of C, then plus A2 times second row, and so on. It's heavily intuitive. I won't go through the exact notation with summations and all that, but I think like that idea is very clear. I mean, my goal here is to go through the ideas, not necessarily do all the problems exactly, right? I want to show with 2 by 2 matrices that matrix multiplication is not commutative. So I'm going to find 2 matrices A and C such that this is not the case. This doesn't seem difficult because matrix multiplication in general is not commutative. This is just a known fact, right? So if you have 1, 0, 1, 1, and 1, 0, 0, 1, that's probably the worst example you can come up with. 1, 0, 1, 0. Like, this is a better example, maybe. Now, if you multiply these 2 matrices together, you're going to get 1, 1, 1, and 1. But what if you do this the other way around? 2, 1. Okay, so you got a 2, so you should already be good. These two are not equal. Well, it's hard to explain exactly why they're not commutative. I haven't really figured out myself, but I think if you apply a transformation first and then the second one, it's gonna be kind of not the same as you apply the second transformation than the first. But yeah, it doesn't really make much logical sense if you say it like that. This is kind of like when you show that in a vector space that a scalar distributes across 2 members of the vector space, or that a member of the vector space distributes into 2 scalars. Something similar like that. Question 13, that is. I think then you want to extract arbitrary entries within this. Let's say B and C have the same dimension, which is m times L, I don't know, and A has dimension n times n, and this is highly arbitrary in general, so this is fine. Now let's consider ij's entry of this, right? So you're gonna have is something like this, perhaps. Yep. And I think like once you arrive at this stage, then the realization is very natural that you can just group them together. And once you group them together, then you see that you can add B and C first and then apply A to it, or you can distribute it with AB plus AC. This is true for arbitrary entries of AB plus Cij, then it's true for the entire matrix. But in the other way around, you got something like this. Now assume these two matrices share the same dimension, n times m, and this matrix has dimensions m times l. And what happened here is eerily similar. Let's say you want to figure out what the i's row, j's column entry of this matrix is. And then what you do is just say something like this once again. That is quite straightforward, I like to think, at least. Adding these two together, you get dir plus dir times frg. And this is just matrix-wise addition, as is the definition of matrix-wise addition. So distribution works fine that way. Yep. Prove that matrix multiplication is associative. Suppose ABC are matrices whose size that ABC makes sense. Yeah, okay. So once again, like, I think it is possible to extract element-wise the elements that should be in the matrix. Choose an arbitrary element and show that the multiplication is associative that way. Shouldn't be too difficult, I don't think. Oh, well, it's going to be annoying because there's 3 matrices involved, so, but otherwise it's not too bad. So you have A times B, B times C, and C times D as your dimensions, right? And then what you have is I'll extract the i's column, j's row. So first you gotta do, because this, in order to extract at the i's column and j's row, this will become, let's say this matrix has dimensions, AB has dimensions A times C. And then what you want to do is perhaps something like this. Where R varies between 1 and C, or no, hold on. 1 and C works. Yeah. And this you can break up, right? It's going to be annoying to do, but you can most certainly do it. Let's use another variable k, right? And k is going to vary from 1 to b, and then this is going to vary from 1 to c times crj. And then if you just put everything together, you're going to get aik, bkr, crj, where k is varying between 1 and b, and R is varying between 1 and C, and I think in fact you can switch those summands, those the order in which you perform those sums does not matter, so you can switch them around. Because you'll exhaust, so you're essentially like taking elements from 3 sets and multiplying them, and multiplication is commutative, so you can just swap them around. But I don't know. That's probably quite a silly statement to say. Alright, consider it this way. Then you want to do A first, or apply A to B times C. Let's say A has dimensions A times B has dimensions B times C, and C has dimensions C times D. And then K will vary between 1 and C for, let's say you want to extract the ijth entry of A times B times C. Then you have something like this, I think. Well, first you don't want to go with the BC first, you want to go with A and BC as a single unit. Otherwise you get horribly confused. Yeah, and then you can break this up in the middle. Let's say R goes from K and then, yep. Now I multiply them all together like this. I think the only difference is I use different variables, but the summons look exactly the same, and so does the structure. I to R, R to K, K to J. This is from I to K, K to R, R to J. And K and R are iterating between 1 and B and 1 and C. These are in fact the same. Yeah, there's nothing much to it. And question 15 just sort of follows from that, where we have a less general case where A is multiplied itself 3 times, or in the previous case we have shown this formula for ABC. I think this you don't really need to go too much into it. It's the same. Alright, so I think that would be it for section 3C. I might come back to section 3D or not later, because we are already up to chapter 4 in certain respects and not in others, because he's going to cover chapter 4 next week. Also, he's already gone through all chapter 3, so I should attempt to finish chapter 3 today or maybe tomorrow. But that's a tall order.